I want to start with a number today, 13.8 billion.
Uh-huh.
That is the age of the universe, give or take a few million years. It's the number that anchors everything we know about cosmology.
It really is. It's the cosmic clock. It defines the boundaries
Okay.
of the entire playground we're studying.
Right. And for the last, I don't know, 50 years, maybe more, we've had a pretty clear schedule for that timeline. The Big Bang happens.
Yeah.
Then the universe is this hot, dense soup. It cools down. Gravity starts sweeping up the mess. And very, very slowly, things get organized. We go from chaos to order.
That's the standard model in a nutshell. It's what we call the bottom-up theory. You start with small blobs of gas, they merge into slightly bigger blobs, and then eventually, billions and billions of years down the line, you get the beautiful structured spiral galaxies we see today.
Exactly. Rome wasn't built in a day, but yeah, I was looking at the stack of research you sent over for this deep dive.
Yes, the weekend reading.
Yeah, specifically the reports from Space Daily, Nature Astronomy, and of course the latest data dumps from the James Webb Space Telescope. And it looks like Rome might have been built, well, instantly.
It is creating a lot of uncomfortable silence in university faculty lounges, I can tell you that much.
I can only imagine. We are talking about a discovery that effectively, I mean, it just breaks the schedule. We're looking at a galaxy that is a dead ringer for our own Milky Way, a twin, but it's sitting in a time period where, according to our textbooks, the universe should still be in kindergarten.
It is exactly like looking at a class photo of toddlers and finding a fully grown man in a three-piece suit sitting in the back row.
Huh. That's a great image.
It just shouldn't be there. It implies a kind of maturity that, well, it completely defies the timeline we've all agreed upon.
So today, our mission is to figure out who this guy in the suit is. We're doing a deep dive into what scientists are calling the crisis in cosmology.
And it is a crisis, but a good one.
Right. We're going to talk about specific galaxies like Ceres 2112. We're going to talk about dark matter scaffolding, supermassive black holes, and we're going to ask the big question: did the universe grow up way faster than we thought?
And if it did, what does that mean for the potential of life elsewhere? Because if the house was built earlier, tenants might have moved in a lot earlier.
Oh, I love that. Okay, let's start with the visual. Let's set the scene. If I step outside tonight, drive away from the city lights, and I look up, I see the Milky Way. It's that spilled band of milk across the sky.
It's a sight that has captivated humanity since we first, gained consciousness. It's our home.
But when we look at it with modern instruments, with telescopes, we don't just see a smudge. We see structure. We see a bulge in the middle. We see these massive spiral arms.
We see a bar of stars cutting right through the center. It's not random. It looks like a precision-engineered machine.
It is a machine, in a sense, a gravity machine.
A gravity and rotation machine, yes. The Milky Way is what we call a barred spiral galaxy. And that structure, the disk, the arms, the bar, that's the result of billions of years of rotational physics. It takes an enormous amount of time for a galaxy to settle.
Settle. That feels like a really key word here.
No, it is. Think of it like a pizza chef tossing dough. When you first mash all the ingredients together, it's just a lump, a chaotic ball of stuff.
Right.
It takes spinning, it takes energy, and it takes time to flatten it out into a smooth, thin disk. In the early universe, we expect to find the lumps. We expect to see the blobs. We absolutely do not expect to find a perfectly formed thin crust pizza.
But then came the James Webb Space Telescope.
Then came the time machine.
Before we get to the specific galaxy, I really want to pressure test the tool we're using here because, we often hear time machine in astronomy, and it's kind of a metaphor. But with the JWST, we are dealing with some very specific physics regarding light. Why couldn't Hubble see this? I mean, Hubble was legendary. It stared at the deep universe for weeks at a time.
Hubble was and is a legend, you're right. But it had a kind of a biological limit, so to speak. Hubble looked at the universe largely in visible light, the same kind of light your eyes can see.
Okay, so it's basically just a giant, powerful eye in space.
Exactly. But the universe is expanding, and this is the key concept for this entire deep dive we're doing, redshift. As space itself stretches, it stretches the light waves that are traveling through it.
So you have a wave of light, and the medium it's traveling through is getting bigger, so the wave gets pulled apart.
Perfectly put. If you have a blue light wave, which is short and tight, high energy emitted by a young star 13 billion years ago, by the time it travels through 13 billion years of stretching space to reach us, well, it has been pulled apart. It isn't blue anymore.
What color is it then?
It's been stretched all the way into the infrared. It's effectively heat. invisible to our eyes, and mostly invisible to Hubble.
So Hubble is staring at this patch of what looks like empty black sky, not because there's nothing there, but because the light has literally shifted out of its vision range.
Precisely. It's there, but it's invisible to Hubble. The objects have redshifted into a frequency that Hubble's detectors just cannot pick up. But JWST is an infrared hunter. It was built specifically to operate in those longer wavelengths.
Okay, but there's a catch to that, isn't there? Something about temperature.
A huge catch. To see these incredibly faint infrared heat signatures from the dawn of time, the telescope itself has to be unbelievably cold.
Because heat is infrared radiation. If the telescope is warm, it would blind itself.
Yes, exactly. It would be like trying to see a candle a mile away while someone shines a high-powered flashlight directly in your eyes. That's why JWST is parked a million miles away from Earth.
At that Lagrange point, too.
Right, at L2, where it can hide behind this massive sun shield the size of a tennis court. It keeps its instruments at, roughly minus 370 degrees Fahrenheit, about 40 Kelvin, just a little above absolute zero.
Just to catch a few photons from the specific galaxy we're about to discuss.
And not just to catch them. There's another huge advantage to infrared.
Which is?
Piercing through the dust. The early universe is dirty. It's filled with this cosmic smog of dust and gas.
Stuff left over from the first supernova.
Exactly. And visible light, the kind Hubble sees, just bounces off that dust to get scattered and absorbed. But infrared light, it has a longer wavelength. It flows around the dust particles. It goes right through, like the dust isn't even there.
So it's like having cosmic X-ray vision.
That's a great way to think about it. It can see inside these dusty cocoons where stars and galaxies are being born.
Okay, so we have this cold infrared sniper rifle sitting a million miles out. We point it at a patch of sky that looks empty to Hubble. We're looking back to a redshift of about, z = 3 or z = 4?
Right, which corresponds to the universe when it was roughly 1 to 1.5 billion years old.
So just a toddler, about 10% of its current age.
A cosmic infant, really.
And based on the Lambda CDM model, the standard model of cosmology, what should we see in that image?
We should see chaos. We should see train wrecks. At that age, galaxies are supposed to be forming through violent mergers.
Rah.
Gravity is just smashing gas clouds together left and right.
So lumpy, irregular.
It should be messy, hot, and completely irregular. There shouldn't be any defined structure yet. The pizza dough should still be a lump, a collection of lumps even.
But that's not what the data showed. Let's talk about Ceres 2112. This is the galaxy mentioned in those Nature Astronomy papers. It's the one causing all the fuss.
Ceres 2112 is the anomaly. It's the observation that breaks the rule. When the data came down and the astronomers processed the images, they didn't see a blob. They saw a barred spiral galaxy.
A barred spiral. Not just a spiral, but a barred spiral. That implies a very specific anatomy, right? Walk us through what that actually looks like.
Okay, imagine a pinwheel, a classic spiral galaxy. Now, instead of the arms coming directly out of the very center point, imagine a straight line of stars cutting right through the core. That's the bar.
A central line of stars.
Yes, and the spiral arms then trail off the ends of that bar. Now, in the modern universe, like in our own Milky Way, bars are common. They're actually really important.
Oh, so?
They act as these incredible funnels. Their gravity grabs gas and dust from the outer parts of the galaxy and channels it into the center.
To feed the black hole.
To feed the supermassive black hole and fuel star formation in the bulge. But, and this is the critical part, they are a sign of maturity, of a galaxy being grown up.
Why? Why does a bar mean a galaxy's grown up?
Because bars are surprisingly fragile structures. They require a stable, dynamically cold disk to form.
What do you mean by cold? Not temperature, I assume.
No, not temperature. Cold in a gravitational sense. It means the stars are all moving in nice, orderly circular orbits. They're not zipping around randomly. If a galaxy is constantly being bombarded by smaller merging galaxies, or if the gas is too hot and turbulent,
Then the bar can't form.
it can't even sustain itself. You'd be shaken apart. Finding a bar in the early universe is like finding a calm, glassy lake in the middle of a Category 5 hurricane. It just doesn't fit the environment.
So let's visualize this. Let's do a theater of the mind moment. If we could strip away the billions of light years and just, park a spaceship right next to Ceres 2112, what are we seeing out the window?
Okay. You are looking out into the darkness of the early epoch. The universe around you is blacker, emptier than today, fewer foreground stars. But then you see it. The first thing you notice is the core, the central bulge. It's intensely bright, a yellowish-white glow.
And that color tells us something.
It tells us it's made of older stars, which is a paradox in itself, isn't it? Having old stars in a young universe. But we can circle back to that.
Okay, so a great, dense city center. What's next?
Surrounding it is the disk. And it's not a fuzzy cloud or a sphere. It's a remarkably flat plane, like a record. And it's on that record that you see the most amazing feature.
The arms?
The magnificent spiral arms.
Oh, yeah.
And they are glowing with a fierce blue light.
Blue means young, hot stars.
Exactly. Blue means hot, massive, and very, very young stars. These are cosmic nurseries, where stars are being born at a rate that would be, frankly, astonishing compared to our own Milky Way today. It's a galaxy in the middle of a baby boom.
But it's not just blue light, is it? I read about the dust lanes.
Ah, yes. Cutting through that brilliant blue light are these dark, jagged streaks, like veins.
The dust lanes.
The dust lanes, that's the raw material. It's the silicates and the carbon, the heavy elements blocking the starlight from behind. Seeing those organized, coherent dust lanes tells you that the rotation of the galaxy has settled.
So it's not tumbling.
It's not tumbling randomly through space. It is spinning like a majestic, stable gyroscope.
It sounds beautiful, and at the same time, it's terrifying for a cosmologist.
It's terrifying because of the time constraint. Physics is not magic. It's a process. To get from a chaotic cloud of post-Big Bang gas to that structure, that organized, spinning, star-forming machine, usually requires billions of years of what we call dynamic settling.
Stars need time to sort themselves out.
The stars need time to interact gravitationally, to calm down their weird orbits, to flatten out into that cold disk. The whole system needs to relax.
And we only have, what, 1 billion years of total cosmic time here. And you have to subtract the time it took for the very first stars and galaxies to even turn on.
Exactly.
Yeah.
You really only have a few 100 million years of build time. To build a Milky Way twin in that time frame is, frankly, impossible under the current models.
So this brings us to the theoretical crisis. I keep seeing this phrase in the papers you sent, the tension, cosmological tension. It sounds like a very diplomatic, very polite way of saying, we have no idea what is going on.
It's a polite academic term, yes,
Yeah.
but the tension is very real. And it all comes down to the lambda CDM model.
Okay, let's unpack that. Lambda CDM, we hear it all the time in these discussions. Lambda is dark energy, CDM is cold dark matter. This is basically the Bible of cosmology right now.
It is. It's our standard model. And for the most part, it works beautifully. I mean, astonishingly well. It predicts the cosmic microwave background radiation perfectly. It predicts the distribution of galaxies on massive scales, the cosmic web. But it has a very strict speed limit on structure formation. It dictates very precisely how fast gravity can pull things together in the early universe.
So Lambda CDM is the traffic cop saying you can't go faster than 55 miles per hour. But Sears 2112 just blew past us doing 200.
That's a perfect analogy.
Yeah.
The hierarchical model, which is a core part of lambda CDM, says you build big things by smashing small things together.
Bottom up.
Bottom up. It's a messy, violent, hot process. And to get a cool, orderly disk, you need to stop the smashing. You need to let things cool down and settle for a long, long time. But in the early universe, the smashing should be at its absolute peak. Everything is crowded together. Everything is colliding.
So how does a galaxy find a quiet corner of the universe to grow up so fast?
That is the million-dollar question. That's the tension. It suggests that perhaps the hierarchical model isn't the whole story.
What's the alternative?
Maybe things don't always build bottom up. Maybe, just maybe, under certain conditions, they can collapse top down.
Top down. You mean a massive cloud of gas just collapses all at once into a ready-made galaxy?
Potentially. A monolithic collapse.
Wow.
Or it could mean that the scaffolding of the universe was much more advanced than we thought.
And this brings us to the invisible architects.
The invisible architects of the universe. Dark matter.
Dark matter, right. You cannot talk about galaxy formation without talking about the halo.
Impossible. The visible stuff is just the tip of the iceberg.
We always describe dark matter as the glue holding galaxies together, because the visible matter, the stars and gas, doesn't have enough gravity on its own to keep them from flying apart.
That's true, but for formation, think of it less as glue and more as the foundation, the blueprint. We believe that every galaxy we see forms inside a massive, invisible sphere of dark matter. We call it a halo.
So the dark matter comes first.
Yes. The dark matter pools together first because it doesn't interact with light or radiation, so it can start clumping much earlier. It creates a deep gravity well.
Like putting a bowling ball on a trampoline.
Exactly. And then all the normal matter, the hydrogen and helium gas, it just slides down into that well created by the dark matter. It pools at the bottom, it gets dense, and ignites into stars.
But in the standard model, these dark matter halos also start small and merge to get bigger, right?
Correct. The hierarchy applies to them too.
But if we have a massive galaxy like Sears 2112 so early on, does that mean we must have had a truly massive dark matter halo already in place way ahead of schedule?
It certainly implies that the dark matter clumped together much, much faster and more efficiently than the model predicts. This has led to some pretty interesting new ideas. There are papers now seriously discussing what's called self-interacting dark matter.
Wait, what does that mean? I thought the whole point of dark matter was that it doesn't interact with anything. That's why it's dark.
Well, we know it doesn't interact with light, and it barely interacts with normal matter. But does it interact with itself?
Like, can dark matter particles bump into other dark matter particles?
Exactly. Does it have its own version of friction or some other force? If it does, it could radiate away energy and collapse into dense cores much, much faster than we thought. If the scaffold goes up overnight, the building can be constructed much quicker.
So the invisible skeleton of the universe might be more complex, more interesting than we thought. But there's another architect involved here, isn't there? The monster in the middle.
The supermassive black hole.
This is one of my favorite parts of the new research from Webb, the little red dots. It sounds so harmless, like a candy, but it's actually something absolutely massive lurking in the early universe.
It is a wonderfully deceptive name. In these deep field images from JWST, astronomers kept seeing these tiny, compact red dots scattered everywhere. At first, they were a complete puzzle.
They didn't look like galaxies.
They didn't look like normal galaxies, and they didn't look like individual stars. But when they used spectroscopy, breaking down the light from these dots, they got a huge surprise.
What did they find?
The light signatures reveal that these aren't just red stars. They are supermassive black holes, actively feeding on gas. They're quasars.
But they're shrouded in something? Is that why they're red?
They are buried in thick cocoons of dust. That's why they look red. All the blue light is being filtered out and scattered away. But here is the real shocker. These black holes are far too big.
Too big relative to what?
Relative to the tiny galaxies they live in. In the local universe, nearby to us, there's a pretty stable ratio. The central black hole is usually a tiny fraction, maybe 0.1% of the host galaxy's mass.
A drop in the bucket.
A drop in the bucket. But in these little red dots, the black hole might be 10%, 20%, in some cases even 50% or more of the total mass of the stars around it.
Whoa, hang on. So instead of a galaxy with a black hole in the middle, it's basically a black hole wearing a galaxy as a coat.
That is a very evocative and very accurate way to put it. And it completely flips the script on how galaxies form. We used to ask, did the galaxy form first and then grow a black hole in its center?
And now
we are seriously asking, did the black hole form first and then pull the galaxy into existence around it?
this is the direct collapse theory I've been reading about.
Yes. The standard story of black hole growth is that a big star lives, it dies, it explodes, and it leaves behind a small, stellar mass black hole. That black hole then eats gas and merges with other black holes over billions of years and gets big.
But we don't have billions of years here.
We don't. We have a few hundred million. You just can't eat that fast. There's a physical limit.
The Eddington limit, right.
Yeah, exactly, the Eddington limit. If a black hole tries to eat too fast, the radiation from the superheated material literally blows the incoming food away. It chokes itself. So to get these monsters so early, they must have started big. They must have been born big.
So what's the theory?
The direct collapse theory suggests that under the pristine conditions of the early universe, a massive cloud of hydrogen gas, untouched by heavy elements, could collapse directly into a black hole, skipping the star phase entirely.
So you just get a black hole that is instantly, say, 100,000 times the mass of the sun.
Yes, a heavy seed. And if you plant a heavy seed like that in the middle of a dense gas cloud, it dominates the environment immediately. It becomes the gravitational anchor for everything else.
And that anchor could be what stabilizes the galaxy so quickly.
Well, it creates a powerful feedback loop. The black hole pulls in gas. The gas, because it has some rotation, doesn't fall straight in. It spins up.
Conservation of angular momentum.
Perfect. That forces the gas into a flat, rotating disk. The disk cools and fragments and forms stars. The black hole, in this picture, is the engine that drives the creation of order.
So the reason Sears 2112 looks like a perfect spiral so early is because it has the superpowered engine in the middle forcing it into shape.
That is the leading theory right now. The supermassive black hole acts as the conductor of the orchestra, bringing order to the chaos much, much faster than gravity acting on its own could ever do.
It's incredible to think about. We usually think of black holes as these cosmic destroyers, but here they might be the ultimate creators. They are the reason the galaxy exists in that beautiful shape.
Destruction and creation are often two sides of the same coin in astrophysics. One star's death is the raw material for the next generation.
Okay, I want to pivot here slightly. We've talked about the structure, the cosmic house. Now I want to talk about the furniture, the chemistry. Because a galaxy isn't just a pretty shape in the sky, it's a place where things happen.
It is a chemical factory on an unbelievable scale.
And to get life as we know it, to get planets like Earth, to get me and you need more than just the hydrogen and helium from the Big Bang. You need metals.
Yes. And it's funny, in astronomy, we have a very simple definition. We call anything on the periodic table heavier than helium a metal.
So carbon, oxygen, iron, silicon, they're all metals to an astronomer.
Yep. The stuff that rocks and bodies are made of?
And the Big Bang didn't make those.
No. The Big Bang was a boring cook. It only made hydrogen and helium and a tiny, tiny pinch of lithium. Every other element you see around you was forged in the hearts of stars and in the explosions of supernovae.
So the logic has always been early universe equals the first generation of stars, which means no metals yet.
That was the bedrock assumption. We assumed the early universe was metal poor.
Yeah.
You might be able to form some gas giant planets, but rocky planets like Earth? Unlikely. Carbon-based life? Impossible. The ingredients just weren't on the shelf yet.
But the JWST didn't just take pictures. It took a spectrum of these early galaxies. It analyzed their chemical makeup, and what did it find?
It found the shelf was fully stocked.
Wait, how is that even possible? How did the ingredients get there so fast?
Well, the spectrometer detected very strong signatures of something called polycyclic aromatic hydrocarbons, PAHs.
That's a mouthful. Break that down for us.
Hydrocarbons. Think complex organic molecules, rings and chains of carbon and hydrogen atoms stuck together. We see these on Earth in soot, in oil, in burnt toast. They're a sign of complex chemistry.
And finding them in a galaxy 12 or 13 billion light years away.
It tells us that the universe got chemically complex very, very quickly.
So the first stars must have lived and died incredibly fast to pump out that much carbon and other heavy elements into the surrounding gas.
It implies a cycle of stellar birth and death that was just frantic. The very first stars, what we call population third stars, were likely absolute monsters, hundreds of times the mass of our sun.
And the bigger they are.
The faster they burn. They would have burned through their fuel in just a few million years, exploded as spectacular supernovae, and seeded the cosmos with the first batches of oxygen, carbon, and iron.
So by the time we get to a galaxy like Sears 2112, about 1.4 billion years in, the galaxy is already chemically enriched.
Enriched enough to potentially form rocky planets. Enriched enough to have the fundamental building blocks of prebiotic chemistry floating around in its gas clouds.
This is where the philosophical shiver runs down my spine. Because if you have a stable spiral galaxy, which is a much safer place to live compared to a chaotic merging galaxy, and you have the chemical ingredients for rock and water and carbon,
then the window for habitability opens up billions of years earlier than we ever thought was possible.
We always have this sort of cosmic arrogance. We assume we are early to the party, that the universe is just getting started with this whole life thing. But this discovery suggests we might be the latecomers.
Or at the very least, we are not the first opportunity. Consider this for a moment. If a planet formed around a sun-like star in Sears 2112, that solar system would be 12 billion years old today.
Well,
our solar system is only 4.5 billion years old.
Imagine a civilization with an 8 billion year head start on us.
It's almost impossible to comprehend. Their original stars would have burned out by now. They would have had to migrate to longer-lived red dwarfs or figure out some other way to survive. But the potential for life to have started back then is non-zero. And before JWST, we all would have said it was basically zero.
That is the paradigm shift right there, from impossible to non-zero.
Exactly. We're learning that the universe appears to be fertile. It seems to want to create structure. It wants to create complexity. It's not a cold, dead void that accidentally stumbled into life after 10 billion years of boredom. It looks like an engine for generating complexity from the very start.
I want to circle back to the twin aspect of this. When we look at this galaxy, Sears 2112, are we seeing our own baby pictures? Or is it more like a sibling that grew up in a different neighborhood?
That's a great question. In a way, it is a look at a potential ancestor. Our Milky Way likely went through phases that looked very much like this. But what is so unique about finding a fully formed spiral this early is that our galaxy has had 13 billion years to settle down.
We thought that was necessary.
We assumed we were what are called late-type galaxies, the end product of a long evolutionary line. The fact that a galaxy could look like us when the universe was only 10% of its current age suggests that the barred spiral shape isn't an end product. It's a robust, preferred structure of nature.
Nature likes the design. It works, so it builds it early.
It works beautifully. It is incredibly efficient for distributing angular momentum. It's efficient for regulating star formation. It's not some fragile thing that only happens at the end of the line. It's something nature wants to build as soon as the conditions are right.
So what's next? This is a huge discovery. We found one. But are there more? Or is Sears 2112 just a total freak accident, a unicorn in the data that we happen to stumble upon?
That is the mission of the next generation of space telescopes. Right now, JWST is like looking at the universe through a drinking straw. It has a very, very narrow field of view. It looks incredibly deep, but it doesn't look wide.
So we could be missing thousands of these just because we aren't pointing the straw in the right direction.
Exactly. We could have a skewed perspective.
Oh.
And that is where the Nancy Grace Roman Space Telescope comes in. It's a NASA mission that's slated to launch later this decade.
I've heard it described as Hubble with a wide-angle lens. Is that accurate?
That's a very good analogy. It has the same incredible image resolution as Hubble, but a field of view 100 times larger. It's not going to drill deep like Webb. It's going to paint with a broad brush. It will survey massive swaths of the sky.
And it will tell us what?
It will tell us if this Milky Way twin is a rare unicorn, or if the early universe is, in fact, teeming with them.
And if it's teeming with them, if Roman comes back and says, hey, there are a million of these things out there,
then we have to rewrite the textbooks completely. We will have to fundamentally rethink the timeline of cosmic evolution. We might have to modify the lambda CDM model itself. Maybe we need to tweak our understanding of gravity or dark energy or dark matter. Everything is on the table.
It's the crisis again. But you seem happy about it. You sound excited.
A crisis in science is just an opportunity in disguise. It's the best thing that can happen. It means there is something profound and new to learn. If the model worked perfectly for everything, frankly, we'd be bored. The fact that the universe is surprising us is the best possible news. It means the mystery is still alive.
And we are also seeing contributions from the European Space Agency's Euclid mission, right? How does that fit in?
Yes, Euclid is a different kind of tool for a different job. It's mapping the geometry of the dark universe. It is taking pictures of billions of galaxies, not to study them individually, but to see how their shapes are subtly distorted by the gravity of the dark matter that sits between them and us.
So it's mapping the invisible scaffolding directly.
Exactly. So between JWST drilling these deep, narrow holes, Roman taking these wide panoramic pictures, and Euclid mapping the invisible skeleton that holds it all together, we are entering an undisputed golden age of cosmology.
It's amazing to think about the technological leap we've made. I mean, just a few decades ago, we were squinting at fuzzy photographic plates with blobs on them. Now we're debating the fine spiral arm structure of galaxies at the literal dawn of time.
It puts humanity in a very interesting perspective, doesn't it? We are these tiny, fragile biological creatures on a small rock orbiting a very generic star in a quiet suburb of one galaxy. Yet we have built tools that are capable of catching photons that have been traveling since the birth of the cosmos.
And interpreting them. We're not just seeing them, we're understanding the physics behind them. We're reverse engineering the universe.
We're decoding our own origin story in real time. Every time we find a galaxy like this, we are learning about the conditions that eventually led to the Milky Way, to the formation of the sun, and ultimately to us.
I want to touch on one specific detail from the sources that really blew my mind. The idea that dark matter might not just be the scaffolding, but could be masquerading. Science Daily had a headline that said, "Dark matter could be masquerading as a black hole at the Milky Way's core."
Ah, yes. This is a fascinating theoretical branch.
Yeah.
It's a bit on the fringe of the mainstream right now, but it's mathematically sound. It's being taken seriously.
So you're telling me we're not even 100% sure the thing in the middle of our galaxy is a black hole?
Well, let me be clear. The overwhelming consensus is that Sagittarius A is a supermassive black hole. We have the incredible image from the Event Horizon Telescope. It looks like a black hole shadow. It acts like a black hole. But science demands that we test every single plausible hypothesis.
So what's the alternative? What could pretend to be a black hole?
The theory is that a super dense clump of a certain type of exotic dark matter, perhaps what's called fermionic dark matter, could mimic the properties of a black hole.
How so?
It would be incredibly compact, it would have immense gravity, but it wouldn't have a singularity at its center.
So no event horizon, no point of no return.
It might have a kind of surface or a fuzzy edge rather than the sharp one-way door of an event horizon.
Yeah.
Now, if this were true, and that is a very, very big if, it would solve the mystery of how these massive central objects grow so fast.
Wow.
You don't need to go through the slow process of collapsing a star and then feeding it for billions of years. You just need dark matter to clump together under its own gravity, which we know it does very well.
It connects back to the scaffolding idea. If the center of the galaxy is just a really, really dense piece of the dark matter scaffolding,
It unifies the two architects, the foundation and the central engine, into one single entity. But again, extraordinary claims require extraordinary evidence. For now, the supermassive black hole model fits all the data best, especially with the jets and feedback loops we observe.
still, the fact that it's even a serious discussion shows how much we still have to learn about the dark side of the universe. I mean, dark matter, dark energy, it's 95% of everything, and we're still just poking at it with a stick.
We are mapping the shadows on the wall to try and understand the light.
Let's bring it all back home. Let's bring it back to the listener. Why should someone who is, driving to work or washing dishes or sitting on the bus care about a galaxy 13 billion light years away? Why does Sears 2112 matter to them?
Because it redefines home. We tend to think of the Earth as our home, or maybe the solar system. But the galaxy, the Milky Way, is our true cosmic city. And understanding that cities like ours aren't some late-stage rare development, but a fundamental feature of the universe, that changes how we see our place in it all.
We aren't an accident of the final act of the play.
No, we are not the encore. The stage was set for us, or for things like us, in the very first act. The architecture for home has existed since the dawn of starlight.
That is a very powerful thought. The universe was building homes long before we were around to even think about living in them.
And it suggests that we are deeply connected to that deep past. The carbon in your hand, the oxygen you're breathing right now.
Yeah.
Some of that might have been forged in a star inside a galaxy, just like Sears 2112 billions of years ago. Blown across the intergalactic void in a supernova, eventually it found its way into the gas cloud that formed our solar nebula.
We are made of star stuff, as Carl Sagan said, but now we know that star stuff was being cooked up a lot earlier in places a lot more familiar than we ever thought.
Precisely. The universe has been making the ingredients for us for a very, very long time.
Before we wrap up, I want to speculate a bit. Pure speculation here. No peer review required. If you could stand on a planet in that twin galaxy 13 billion years ago, what do you see when you look up at the night sky?
Oh, wow. You would see a sky far richer, far more dramatic than ours. First, the universe was smaller then, everything was more crowded. You might see other large galaxies much, much closer, appearing huge in the night sky.
Like having Andromeda fill up a quarter of the sky.
Maybe even bigger. You'd see them actively interacting, maybe merging, with streams of stars connecting them. And then the stars in your own galaxy would be overwhelmingly young, burning with that brilliant blue and white light.
So a much brighter sky.
Much brighter. And the rate of starburst would be so much higher, so you'd see these vast, glowing nebulae, the star factories, splashed all over the sky in brilliant pinks and reds. It would be a dazzling, energetic, almost violent night.
A sky on fire with creation.
A very dynamic, very live sky. But, and this is the paradox, you would be standing on a stable platform, a calm spiral arm, a safe harbor in a violent cosmic ocean.
That is a beautiful image. It makes me want to go there.
Well, in a way we have. JWST has taken us there. We've seen it.
The ultimate time machine.
And we are only in the first few years of its mission. Imagine what we will find in 5 years, or 10.
Or what Roman will find when it starts its survey. Or what Euclid will tell us about the dark matter map. The map is getting bigger and more detailed every single day.
The map of our universe is being drawn in real time right in front of our eyes.
It really feels like we're living through a genuine paradigm shift. I know that phrase gets overused in science, but from chaotic blobs to ordered spirals, from a metal-poor and lifeless early universe to one filled with complex hydrocarbons, the entire narrative is changing.
It is. We're moving from a model of a slow, stumbling, almost accidental universe to one that appears to be rapid, robust, and incredibly creative from its earliest moments.
So as we sign off, I want everyone listening to go back to that opening image. Tonight, if it's clear where you are, go outside. Look up. Find that milky band of light that is our galaxy. But don't just see it as it is now. Try to imagine its twin. a ghost, shimmering in the deep infrared billions and billions of years ago. A mirror image of our home, standing tall and beautiful at the dawn of time.
We're not alone in structure, and it seems we may not be alone in time.
That is where we will leave it. The universe is bigger, older, and strangely much more familiar than we ever dreamed. Thanks for diving deep with us.
Always a pleasure. Keep looking up.
And stay curious. We'll see you on the next deep dive.